Hey everybody, welcome to Lecture 9b. So today we're going to cover Chapter 6, Section 4, and this is all about our companion, the moon. And it's, of course, this whole chapter is about Earth, so it's a good place to talk about the moon, but just remember that the moon, we kind of lump in with the terrestrial planets, right? So it's very cool that we have such a big moon. We've talked about that. And that it's so close to us, and we've been able to do things like leave seismographers on the surface of the moon. So little not seismographers, not the people, but seismographs on the moon, so we can look at things like the vibrations of the moon. We can simulate earthquakes on the moon and look at those P waves and F waves and really learn about this other world, which is the moon. But the moon also has a lot of influence on the Earth. And we're going to first talk about high and low tides, which are some of the biggest influences on the Earth. Okay, so this is really in the context of the Earth. All right, so you probably all have heard of tides, and you may have, if you've ever lived near a coast, seen tides, right? Low tide and high tide. And seeing the effects of tides, or maybe even watched a tide come in. When I was a kid and we used to go to the beach, we would be there all day and we would see the tide come in. And so that was, it's really cool to watch. So the tides are really an effect of the gravity of the moon. And as we're going to see as well, also from the sun, gravity from the sun, right? And so you can see in this little diagram here that if you look at where the moon is, right, it causes a bulge in the water, and that water is going to sort of move towards the moon. And this one's a little harder to understand. We're going to see a video on this in a second that shows you, but what's happening is it's pulling the Earth a little bit this way, and so you get this bulge also on the opposite side. And here you get these low tides on, sort of on this, 90 degrees away from the moon, right? The moon Earth line. And this is due to what's called tidal gravity, which sort of stretches in one direction and squeezes in the other. And we're going to see a little bit more about that in a couple of videos. Again, the sun is actually also contributing to tides. So let's see a video. So this should be hopefully get this whole idea of this interaction between the moon and the sun and the tides a little clearer in your mind. All right, so let's go to a video. Here we go, full screen.
This shows 12 hours at the famous Bay of Fundy in Nova Scotia, Canada. It's the biggest tide change in the world. But what force could move such a massive body of water? Gravity. Here's the Earth rotating on its axis every 24 hours. We'll now draw the Earth as a diagram with its surrounding layer of ocean. And to the right is the silvery moon. Everything is attracted to everything else in the universe with the force of gravity. So the moon is attracted to the Earth, and the Earth is equally attracted to the moon. Notice that the two force arrows are the same length, showing that gravitational attractions are of equal strength. But we're only interested in the force on the Earth here. The moon pulls on the ocean closest to it and makes it bulge outwards. When the Earth rotates, the sea level is higher at this point in its rotation, causing a high tide. And a low tide where the oceans don't bulge. So you'd expect one high tide each day. But here it gets interesting because there are 2 high tides a day. How come? This is because the strength of gravity is greater when objects are closer. We'll call the location of the ocean on the near side of the Moon, point A, at the centre of the Earth, point B, and at the far side ocean, point C. The strength of the Moon's gravity is strongest at A because it's closest to the Moon, so the part of the ocean that bulges towards the Moon most is at A. But the Moon's gravity also pulls on the Earth, moving it towards the Moon as well. This has 2 effects. First, it makes another bulge at C. Second, it fills in the bulge at A, but not completely, because A has moved further towards the Moon than B. Lastly, the far side ocean at C is also attracted to the Moon, but it moves least because the Moon's gravitational pull here is at its weakest, being farthest from the Moon. This leaves a partial bulge at C, though not as big as the one at A. Now we can see why, when the Earth rotates through 24 hours, it goes through 2 high tides and 2 low tides. But there's another surprise. By the time the Earth has rotated once and arrived back at its original position, the Moon has moved on a bit because it's orbiting the Earth at the same time. That means that the Earth has to catch up with the Moon, so the next day's high tide is about 50 minutes later. The Moon rises and sets about 50 minutes later too, because the Earth has to catch up with its orbiting Moon. You can even test this by timing the moonrise or moonset from one day to the next. Or check out some tide charts to see if the tides obey this rule too.
Okay, so let's see another video that goes into more detail about how, well, this first video didn't say anything about the sun. The sun also contributes, so let's see about that. And that's where the words spring and neap tides come from that you may or may not have heard. Okay.
Tides are caused by the Moon's gravitational force pulling on the Earth and its oceans with different strengths. The pull on the near side ocean is the strongest because it's the closest, so it moves most towards the Moon. The Earth also moves towards the Moon, but not so much as it's further away. Finally, the far side ocean moves towards the Moon least because it's farthest from the Moon. These movements due to gravity create 2 high tides and 2 low tides as the Earth rotates through 24 hours. But there's a big object that's missing from our diagram. If we back up, we can also see the Sun and how it lights up both the Earth and the Moon into their day and night sides. We'll turn off the stars to make it clearer. When the Moon is right in front of the Sun, it's invisible to us because we can only see its dark night side. This is the new Moon position. You can see that each day corresponds to 1 Earth rotation. In just over 7 days, that is 7 Earth rotations, the Moon orbits around the Earth to its first quarter position, where we can see half its day and half its night side. After another 7 days or so, the Moon orbits to the opposite side of the Earth to the Sun, and we can see its full day side. This is the full moon. Then it continues on to the third quarter, before returning to the new moon position to start all over again. Does the sun also pull on the oceans and make them bulge like the moon does? Yes, everything causes gravity, and the more massive the object, the stronger it is. But this diagram isn't to scale, and the sun's much further away than the moon, reducing its tidal effect to about half that of the moon's. But this is important when the sun and moon line up so their gravitational attractions combine to make super tides. This happens at the new moon, making the high tides higher and the low tides lower. This extreme tide is called a spring tide. But when the moon goes into the first quarter, the gravities pull in different directions, and the sun actually takes away from the moon's tidal effect. The high tides are not so high and the low tides are not so low. This more moderate tide is called a neap tide. At the full moon, the moon and sun's gravities line up again, so we get another spring tide. At the third quarter, the gravities are out of whack again, so we get another neap tide. Then back at the new moon position, the moon's gravity combines with the sun's to start over again with another spring tide. Each month, the Earth spins almost 30 times, so we get nearly 60 high tides and 60 low tides. Of these, 2 are spring tides and 2 are neap tides.
Okay, well, I hope that was relatively clear on what causes not only tides, but the special tides, spring tides, and neap tides. So this is gravitational interaction between the sun, moon, and earth, and of course the earth's oceans. And the reason that they can bulge out like that is, of course, that it's water, and you can sort of pull on water and make it move, right? Less than you can, if pulling on a rock is not going to make it bulge. Although we're going to see that these sort of tidal kind of forces can have an effect on a planet or moon's crust, and we'll see that with Mercury. Okay, all right. Now, what other effects does the moon have on the Earth? Well, that's a really interesting one, and that is that over time, Earth's day length is going to change because of these tidal forces. Now, how it does that is pretty complicated to explain, but it's because the bulge is not quite aligned between Earth and Moon, and so you get this sort of almost like a friction effect that's going to slow down Earth's rotation. Now, it doesn't slow it down that much, and as you can see down here on the bottom of the slide, it shortens the Earth's day, by 0.0017 seconds per century, right? But you put that together with a lot of time, you're gonna have some big changes. So for instance, in about 500 million years, we'll have about an extra 2.5 hours in our day, right? So who knows if there's going to be humans around in 500 million years. Um, if I were a betting person, I would probably not bet on us, but, got to be optimistic, I suppose. But those humans, or whoever, are going to have an extra 2.5 days, hours in the day. Maybe they'll spend it, sleep. I guess you'll sleep for half of it, I suppose. So maybe you'll get a little more sleep. So very interesting that this is what's happening. And it's going to continue to happen as time goes on. Okay, what else? Well, there's some effect on the moon as well from the Earth. Okay, now you might have noticed that there is, when you look at the moon, and I know that those of you who are in the lab class have been looking at the moon all semester, all the session, right? So you have been going outside and looking at the moon when it's not raining like it is today. And I hope that you notice that no matter what phase the moon is in, the moon pretty much looks the same. So, if you see the old man in the moon or the rabbit, a lot of people see a rabbit in the moon. If you don't know what I'm talking about, go look at your lab. If you're not in the lab class, go look it up on the web. There's these little, characters that people see in the patterns of that light and dark that we see on the moon. Now, you might notice that you never, that face of the moon is the face that's always pointed towards us, right? And this has kind of given us this idea that there's there's a dark side of the moon, right? That somehow the other side of the moon never sees the sun. This is why it's called the dark side. And you might know a very famous song by Pink Floyd about the dark side of the moon. But actually there really is no dark side. It's just that the moon is tidally locked. So tidal forces from the Earth's gravity have slowed the rotation to the point where the moon rotates once every time it goes around the Earth. So if you can imagine, right, so look at this little diagram with the flag. So if you start off, let's say we'll start off here, right? We're going this direction. The moon is going to rotate this way, but if it rotates just the right amount, it'll keep that flag pointing towards the Earth. Rotate just the right amount, the flag will still point at Earth, right? This is called tidal locking, and it's due to these tidal forces from the Earth. And we're also going to see some tidal locking, sort of tidal locking, from the sun, due to the sun on Mercury. Okay, so that's why we only see this one side with those really sort of iconic, what we think of now as iconic. We don't see the other side of the moon. But that other side of the moon is certainly not dark. Think of the new moon, when in this diagram you would have the moon here and say the sun over here, right? And here's the Earth. The sun is shining down on that quote-unquote dark side, on the side that we don't see, right? So all of the moon does actually get sun. There is no dark side. But there is a side that we don't see regularly. And you'll see in a little image that I'm going to show you in a second that, we didn't know what that other side looked like, right, until we could fly something around the moon, right, because we could never see it from Earth. So you can see here, there's, and now people call it the near side and the far side. Is what astronomers call it, not the light side and the dark side, okay? And you can see, like here, there's the sort of rabbit thing here, which is like, this is the head, the bunny ears, and the body of the rabbit. I don't really see the rabbit, but some people do. And so this is the side we're used to seeing, and this is what the far side looks like, okay? Very highly cratered, and pretty different, I would say, than the side that we're used to seeing. And this is kind of a topographic map, right, where the color tells you how high up the features are. Notice the blue features are low, right? So with reference to whatever zero elevation is on the moon, they're low because they're kind of like basins, and then the things that are redder are higher, right? Okay. All right, so let's talk about those craters. So on the moon, there's many different kinds of craters, and these were formed somewhere between 4.1 and 3.8 billion years ago. So, well, I should say it the other way, 3.8 to 4.1 billion years ago, during the time that people call the late heavy bombardment. So this was happening as the solar system was forming. There was a lot of junk flying around, and it was whacking into objects, including the Earth. Um, and the reason we don't see all that stuff going, we don't see a bunch of craters on the Earth, and we do see some craters, is that we have lots of things, geological things that are moving to sort of erase those craters. And we have water flow, we have wind, and we have lots of things that kind of erase the craters. But on the moon, no atmosphere, really no geologic activity. We see these craters just stayed forever, right? And you can see some features of craters. Like here, you get a little peak in the center, and that's from molten. You have a something hitting, right? Asteroid hitting the Earth, small meteor, and what happens is in the center, there's so much heat from that impact that you melt the center and it kind of plops up, right? So think of like throwing a pebble into a pond. You get that sort of plopping up in the middle, right? You've probably seen pictures of that, or seen it yourself. And you also get this terracing, right? Which is like material sort of being blown up the sides, right? Again, like if you dropped a pebble into a pond, you get that sort of side motion all around the center that makes these little terraces. And then you get rays as well. You can see rays coming out here, and this is just from material flying off, right, during the impact. So we can tell a lot about the size of the object that hit the moon, etc., from all these craters. So lots and lots of craters with lots of features. Now, let's go back a tiny bit to this guy here. So you can see these little, these really smooth areas that are making the rabbit, right? They're very low, then these basins. They're called maria. And the reason they're called maria, you might remember that mar is the word for sea, right? So for instance, there's cities called Corona del Mar, right? Which means, crowned by the sea. So people, when they first were looking at the moon, they look like oceans. When you look at a picture of the moon, if you go up and look at the moon, they're dark, they're smooth. People maybe thought, maybe there's oceans or lakes on the moon. Of course, that's not the case. But they look that way, so they were named Mar. And now we say Maria for the plural of those. Now, how did those form? Notice there's some over here, but there's really just a lot on our side. Okay. So how did they form? Well, it's really kind of cool. So what happens is you get this big thing, an asteroid coming in, hitting. And what happens is it sort of cracks the surface low enough down that you're going to get a little bit of lava flow up into this area, which kind of spreads out and when it cools, right, it becomes this rocky, smooth thing that kind of looks like a lake, but it was actually a little lake of lava for a while. So that's the formation of the Maria. Those got some really beautiful features on the moon. So you can see that we have, lowlands, which are the Maria. We have highlands, which are the, heavily cratered. You can see that in reds. And the near side shows Maria, while the far side really doesn't show there many Maria. Right? There's a couple little places, but mostly cratered. Now, like I told you before, we do have information about what the moon is made of, and here it is compared to the Earth. And that's from seismographs that were left on the moon, and then simulated earthquakes by, we crash things into the moon to create these little simulated earthquakes. And by looking at those P waves and F waves, we can get some idea what's inside the moon. And the interesting thing about the moon is that it does have a molten core. Right? Remember, we have the structure of the Earth has this solid iron and then a molten iron thing around it. That's part of the core. This is all part of the core. But it's much smaller compared to the radius of the moon than it is for the Earth, right? This is a much bigger core compared to the radius of the Earth. So remember, this molten iron core is what is giving us our magnetic field. And the moon really has a tiny, weak magnetic field. And we think this is because the core is so much smaller relative to the size of the moon. So it really doesn't have much going on geologically either. Okay, now how did the moon form? So this has been a big argument for a long time, and we, especially after going to the moon and collecting rocks and understanding the composition of the rocks, we've been able to really nail this down. But at first, right, there were two big hypotheses, and that was the capture hypothesis, which was in the early part of the solar system formation, there was things zinging around, and maybe the moon came in, right, and it was just captured by the early Earth. The early Earth is this molten-y thing right here. But the problem with that is that it's actually super hard to capture anything that way, especially anything moving past the Earth being captured by gravity. The Earth's gravity is not that strong. It would be a lot easier to understand if it was, say, Jupiter capturing things. It's actually kind of hard. So this object would have to have been, flying there at exactly the right angle and the right speed, and that's pretty unlikely given that things were kind of randomly moving around in the early formation period of the solar system. Now, there's another one called the fission hypothesis, in which like some object was pulled some of this molten Earth into orbit, which cooled and formed the moon. But the problem with that is that the Earth was never like a big ball of molten rock. That was never the case. It actually had a mostly solid, even from the very beginning. Yes, it was very hot and had to cool down. There was a lot of molten stuff, but you couldn't have pulled a big ball the size of the moon off of there like silly putty or something. So neither of these were very good. And it wasn't until later that we came upon the impact hypothesis, which is really there's a lot of good evidence now that this is what happened. So we think that early Earth was struck by an object like the size of Mars. Okay, so Mars is about 50% the size of Earth. That's a big rock, right, hitting the Earth, early Earth, and the debris from that quickly just coalesced and started to orbit, because that's what debris would do, right? It's not going to go off. Some of it may go off flying into space and never return, but a lot of it is just going to start orbiting. And over time, it's going to coalesce under its own gravity and become round, right? We talked a little bit about that, becoming round under its own gravity, and become the moon. And this has become the accepted hypothesis for how the moon came to be. And really, because we could get rocks from the moon, we understand that there is the amount of iron, the relative lack of other things like the lack of potassium, and this is because an object that blew this rock off did not blow it off from the core of the Earth. It didn't go that deep, right? It was blowing rock off from the mantle of the Earth, and so there's sort of this lack of iron in the moon rocks compared to Earth. And we think that's why. So there's a lot of different evidence. I'm not going to go through all of them, but this has become the accepted hypothesis for the formation of our moon. Let's try a question. So pause your video and answer the question.